So yeah, so the talk is different from yesterday. Yesterday I talked a bit about sort of high-dimensional data sets which are intrinsically low-dimensional, and some ways of measuring that, and some ways of constructing sort of global embeddings of high-dimensional data sets down to low dimensions. What I wanted to talk about today is still related to geometry of data, and in fact, I think there are two slides in common with yesterday, the very first two on PCA. And then I wanted to talk about the problem of trying to represent data efficiently. So we're still going to talk about high-dimensional data that somehow has low intrinsic dimension, but the goal is really sparse representation for this data. And I want to talk about this rather generally, but one instance of data that I particularly care about comes from imaging, image patches, for example, from a large collection of images. And that's going to be my only and rather feeble connection to biology in this talk. I like to look at very different type of data sets. Some of the ones I'm looking at a lot nowadays are hyperspectral images. These are images where at every pixel you have a large number of colors, hundreds of colors. For example, also in the near infrared. So at every pixel you can get chemical information. You can decide what kind of chemistry is going on at the pixel. I'm looking a lot at molecular dynamics data, which I also mentioned yesterday. These people run very expensive and long numerical simulations for molecules of interest, both in chemistry or in biochemistry especially, and in the pharmaceutical industry, and they're interested in the properties of these molecules. And the state space of these molecules is very, very large because the number of atoms is very, very large, and so these molecules have a lot of degrees of freedom, and one is interested in extracting the main degrees of freedom of that molecule, especially at large time scales. So if it's an enzyme, when does it open up and catalyzes a reaction, and when it doesn't, or when a protein is folded, when it's not folded, what are the mechanisms there? I like to look at graph data as well a lot, albeit I'm not going to talk about that today. So, and this is going to be my only slide, which was in common with yesterday, but I do need singular value decomposition today as well. And so, and this also sets my notation for other things, so I think it's useful anyways. And so I'm gonna think of my data as lying in RD for very large D. And for example, in the case of hyperspectral images, I could think of every pixel, and it's 100 colors as one high-dimensional vector, and then in every image I have maybe 1 million pixels. That would be a point cloud of 1 million points in 100 dimensions, and I could think of stacking them in a matrix which is d by n, d the dimension, and n my number of samples, so one sample per column. And in the case of the molecule, one column would be the XYZ coordinates of all the atoms in the molecule, and the n would be easily in the millions of hundreds of millions time samples when they run these long numerical simulations of the molecules. And I'm interested in finding somehow low-dimensional models for data, and perhaps the simplest one is just saying that the data lies on or very close to a low-dimensional plane. And one stable way for finding such a plane is to do the singular value decomposition, which is writing X as the product of three matrices, U and V orthogonal and sigma diagonal, with entries called the singular values, sorted in non-increasing order and all non-negative. And if you look at the columns of U, the first column of U is the direction of maximum variability of the data. The second column of U, which is orthogonal to the first, is the second direction of maximum variability of the data. So if your data has variability in a small number of dimensions and very, very small variability in all the other dimensions, so the data would look like a sort of pancake, then the SVD would reveal what those dimensions are. And it will give you a nice orthonormal basis onto which to project the data. So if the data is long in some direction and thin in others, this could be just one direction, or it could be k directions, k much smaller than large D. And then you could project onto those directions spanned by the first k columns of U. And in all the other directions, the data has small variability, and you could interpret that as noise and project it out. All right, and as I mentioned yesterday, and again, that's the only other slide from yesterday, I think. This model typically does not work, but it's extremely simple to understand. There are efficient algorithms for doing these computations, but it's just geometrically very restrictive. It's just saying that the data is close to a low-dimensional plane. So you can try to generalize this to manifold models, which is what I briefly discussed yesterday. But you can also generalize this to saying, well, maybe instead of just one plane, there are multiple planes near which the data lies. And in a certain sense, you know, a curved object might be well approximated by a certain number of planes. And so the two models might not be as different as one might think, albeit classically in the way that research was done in the past 15 years, these have been considered very separate routes. And today I'm going to take the second route, but I'm going to sort of sell you the problem in a completely different way. It's motivated very differently. But in the end, we will see that what we're going to end up doing is exactly constructing low-dimensional models of the second type. So the representation that I'm going to discuss today, I'm going to be multiscale. Multiscale means many different things to different people. Already scale up here briefly in the previous talk, where you can talk about analyzing an image at different resolutions. This will appear in this talk, but this is not what I mean by multiscale here. The multiscale that we're going to do here is about looking at a large point cloud, a large set of points, say all the spectra in a hyperspectral image, or all the patches in an image or in a collection of images. And in this space, in this high-dimensional space, we're going to divide this space into groups. And we're going to analyze these groups more or less independently. And these groups will have different sizes. And the scale will be the scale or the size of these groups. So let me motivate everything in the following way. So the first problem that I want to consider is the following. I'm going to think of my data as being samples from a probability distribution. So if these are patches of images, I'm going to think of, I take some pictures through some process, which you can think of, as rather random. And I'm going to extract patches from them. And so each of the patches is going to be considered a sample from a probability distribution. I'm going to call my sample x size, I from 1 to n, consistent with the notation before. And if you want to think in terms of matrices, each of the x size is going to be a column of my matrix. The probability distribution I'm going to call mu, and it's, of course, in RD, in high dimensions. What I would like to do is doing what sometimes is called dictionary learning. I want to construct a set of vectors in RD, a dictionary, which I call phi. And I'm not going to tell you more about that later, but I want to construct a dictionary for the data, and I want to use the dictionary to encode the data. So I want to construct a map that takes data x and gives you some encoding of that data in a lower dimensional space, Rm. I'd like to have m much smaller than capital D. And so, the data comes in, it gets encoded in some way, and I would like this encoding map to have an inverse. And so that ideally, if I encode and then decode, I get back my point, my original point, or a good approximation to my original point. And I would like that this map compresses things. So I would like the representation dx, the encoding of my data, to require very few bits, much fewer than the ones that I needed to encode my original data d. And then I want to talk about a second problem, which is, so in this way, data will be compressed. We will be able to compress the data efficiently under suitable assumptions of the data. But compression is not all. I mean, we might compress data, but really, the data are just samples from a probability distribution mu. So it would be even nicer if we, instead of just approximating the data well, we could approximate mu well, the probability distribution that generates the data. If we can do that, then all of a sudden we can do all sorts of things which wouldn't be possible in any other way. For example, if we get a new data point, we can ask, is this data point like the others? In the sense, does it look like it's really drawn from mu? Or maybe it's drawn from a different probability measure. If it's drawn from a different probability measure, or if it's extremely unlikely according to mu, maybe we can flag the point. It's an outlier, it's an anomaly, it's something strange. Or we could even do weird things, such as producing new points. If we have an approximation to mu, we can use our approximation. I'm going to call it mu x, because it depends on some training data x. It's a probability measure in RD, we can sample from it. And so what I'm showing here is are pictures, which are pictures of handwritten digits. and that were produced in the following way. There is a database of such pictures. Such database was fed to an algorithm that learned an approximation to mu, the probability measure that generated these images. Each of these images is a point in 800 dimensions, and we produce a probability measure in 800 dimensions, and then we sample from it. And when we sample, we get digits. And these digits are not like the ones in the database in a measurable way, right? I have to tell you that I'm not just reproducing the database itself. And they look reasonable. They look like handwritten digits. And so, I'll be telling you of some ways in which way we did this. And I really care about things which are implementable by fast algorithms. The data is large, it's high dimensional. We need to have these things scaling very well with the size of the data. So I'm not going to talk about constructions that cannot be implemented by fast algorithms. I'm interested in algorithms that have guarantees, theoretical guarantees. What do I mean by that? I'll be telling more, of course, much more about this. But for example, in the case of dictionaries, I would like to be able to tell you things such as, if you have this much data today and it comes from a probability mu satisfying certain assumptions, then I'm going to construct an encoding map which is good in a quantifiable way as a function of the size of the data, the ambient dimension perhaps, and some other property of the probability distribution mu. And one of the goals would be to defeat the so-called curse of dimensionality. It's very hard to work directly in high dimensional spaces in RD. For example, tasks such as approximating a probability measure in RD are just hopeless, as I mentioned yesterday. And the reason why we will be able to do this is that we will be working with probability measures which live in our capital D, but are in fact concentrated near low dimensional sets in a way which I will define precisely. And then I would like my algorithms, my guarantees, to only depend on the intrinsic dimensionality of these sets, not on the ambient dimensionality. And this is what I call in this context defeating the curse of dimensionality. So let me talk more about problem 1. This is the connection with biology, and already Field was already mentioned in one of his papers in the previous talk. So when they looked at the receptive filter for the visual cortex, they asked the question: are the patterns that we have in the visual cortex, can they be explained by asking that they compress the data well, the visual stimuli well? And so they said, well, let's look at lots of image patches, and let's try to find a set of responses that compress the set of patches well. And they wrote down an optimization problem formalizing this, and I will have a short description of those in a moment. And they solved the optimization problem, and the receptive fields that they got, they were blob-like. They had angular selectivity. They looked like, so some of them were blob-like, some of them were like Gabor functions with a Gaussian-like envelope, if you want, and even more interesting, they had directional selectivity. So some of these Gabor functions were oscillating in a certain direction, in other directions, and so on. Exactly sort of as described in the previous talk and as described by the experiments in biology. And so essentially the key here was maybe we can explain the receptive fields in the visual cortex as optimizing a function which is essentially which likes efficient encodings of patches of images. And so you can ask this question in general in the following way. So you see endpoints, those could be the patches of images, but in fact I'm interested in the case where these endpoints might be n text documents, n spectra in upper spectral images, or n molecular configurations. So you see endpoints, and I would like to construct a dictionary that's just a set of m vectors in RD. So m is going to be the size of my dictionary. So I want to construct m vectors in RD such that I can do two things. One is that every one of my data points can be well approximated up to some accuracy epsilon by taking linear combinations of those dictionary elements. So alpha I is a set of coefficients, m of them, So this alpha I is the set of coefficients in a linear combination of the columns of phi. So phi times alpha I is just a linear combination of the elements of my dictionary. And I want to say that for every data point, I can find a set of linear coefficients such that phi times the set of coefficients approximates very well the data. That's requirement number 1, accuracy of the representation. Requirement number 2, I really like set